Hello, I'm Will. Welcome to ResearchPod. The dream of nuclear fusion as a source of near unlimited energy is decades old, but with the latest advances by research teams working around the globe, it may just be within reach. Today, I'm speaking with Dr. Tamás Biró of the Wigner Research Centre for Physics about his team's research on laser ignition of nanoparticles to bring that goal closer to fruition. Tamás, good afternoon and hello.
Hello, how are you doing?
I'm very well. Thank you for joining us. And for everyone listening at home, could you tell us a bit about yourself, some of your academic history, and kind of what's led to your research and kind of how you got into high-end particle physics?
My name is Tamás Biró. I started my academic career with a diploma in physics and biophysics. And then I changed for nuclear physics, more nuclear theory and high energy nuclear theory for my PhD work, which I have done in Budapest. In 83, I left. I visited Niels Bohr Institute in Copenhagen, then GSI in Darmstadt. I spent there 2 years. And then following about 9 years at the University of Gießen in middle of Germany. And then I returned to Budapest in 94. And since then, mainly I was involved in theoretical statistical physics, particle physics, and nuclear physics research. And I was also leading research group, was a vice director of the whole Institute for Particle and Nuclear Physics. And lately we started a new project about 2 years ago about the nanoplasmonic laser ignited fusion experiment that makes the abbreviation of NAPLIFE as a short mnemonics for our experiment.
I've got to say, traveling the world and solving nuclear fusion, you do sound a little bit like a hero from a spy book or a sci-fi
Oh,
series.
wow. I mean, this is the way how such research is done and can be done. I mean, without international communications and connection and getting also personal relations among each other, I don't think in a human way you could do it. I mean, of course, this is a random walk, so to say, that you never know at the beginning of your career where your next stop will be. But such questions like getting inside the proton by experiments, you can do only in international cooperation. No country, not even the USA, can do it alone, really. Actually, they canceled the big accelerator plan in 90s, early 90s or when in Texas to build them. They have a few others. And then we have at CERN, the European Centre for Nuclear Research in Geneva, but near to the French border, this big laboratory, which is now even the Americans are taking part in it. And people from almost everywhere. The frontier science you cannot do in the normal way with blocking people or hatred between the blocks or whatever. You have to cooperate. If you don't cooperate, you don't get a little step further. So, I mean, this is a very special profession, if you wish. So, we are 20, 30 years ahead of other fashions. So, we cannot allow ourselves to look at pigmentation or the haircut of the others when we have to work on really tough problems. It is impossible. We can understand that other people don't like new things, don't like alien things, don't like if someone has some dialect when talking the international English, but in science you cannot do that. That's the only hope for science, that everyone does it and everyone will be judged according to the merits and contributions, not by anatomical or racist or whatever, gender or whatever they do in their life in private. It's private. That's another question. But they are judged by their merits in the common science project, nothing else.
Well, thinking of nuclear energy in the kind of the more all-encompassing terms, it does have something of a reputation, shall we say, on the kind of the international and global stage. There are some conceptions of its usefulness or its safety. And do you see that having the fusion reaction work going on Is that, to you, a remedy to those concerns, or do you think it might just be a new concern for people to have?
I think the main concerns or the most frequently heard concerns are with radioactive material which is made after producing nuclear energy. But all working reactors are based on nuclear fission, not on fusion. So in that case, it's very often that you are left with some more or less radioactive material at the end of the reaction. And then the problem is what to do with them. The one thing is, of course, that they could be reprocessed. But many people were politically against reprocessing because reprocessing also changes the isotopic ratios and can be used for atomic weapons. So anything you use in technology, of course, also can be used as a weapon. The moral dilemma and question is always whether you stop research or you want to know everything more in order to make the right decision. The fusion is better in several senses. Fusion does not need heavy elements and does not make too heavy elements. And the very heavy elements are typically very long-lived radioactivity. So at most they have short radioactivity. But if you are designing very carefully, if we shall have control on what fusion reactions we want, so there is a magic word, probably not yet known in the public, but researchers are talking about. This is neutron-less fusion. If you don't have the energetic neutrons coming out, in the main fusion reaction, which people want to reach first, like ITER, there is deuteron and triton, the second and the third element colliding, but they make very energetic neutrons at the end. 14 MeV per one neutron. Believe this is a high energy, and this is going to destroy the device which keeps them. So there are such problems still on the fusion part. So what very nice would be to go over at the end to such fusion reactions which don't make so energetic neutrons or even neutron-less.
Do you ever find yourself walking around the equipment or talking with teams and saying words like laser accelerated proton physics for nuclear fusion and just have the thought of, I have the most science fiction sounding job in the entire world?
Of course, I was also loving to be near of them. Yeah. Calculating for experiments at the highest energy made on Earth artificially, or now we are going to manipulate almost atom by atom or hundreds of atom level targets of laser shots in order to harvest some, or let's say to tame fusion. To tame fusion means that it's just made in small steps without explosion, without very high temperatures for a short time, but still harvesting extra energy from inside. I think this is the most promising version of doable fusion. You know, most of the physicists and theoretical physicists think that they can do everything. I mean, it's word by word, virtually everything. So, of course, my role in this is not being a plasmonics expert. Also, plasmons I also calculated in the so-called quark-gluon plasma for decades, but this is another matter, and it is made at much higher energies in Large Hadron Collider at CERN, and it's some predecessors of that. But plasma is a phase of matter, some people call it the force phase, when charges separate and they propagate somehow freely in the plasma. So this is also means in the normal atomic plasma means that the electrons are stripped from the atoms, right? Atoms are positive charges, electrons negative charges, and these two coexist in a piece of matter. That's the normal plasma, what we used to have in, well, plasma TV is no more fashion, but we had that trial before the LED TVs, and it was used in all these neon lights, actually. A normal plasma is low density and very high temperature. It's beyond the gas. You may think it is a gas, but this is beyond the gas because there are charges. The atoms and the rest of the atoms with a few electrons or just the atomic nuclei are freely moving from their outside electrons. This is the normal plasma. But in a general sense, we call everything plasma when you have different charges freely moving away from each other. And fusion is at so high energy actually that in fusion, nuclear fusion nuclear means that only the atomic nuclei make the reaction with each other. So atomic nuclei consist mainly of two particles. One we call proton, because this is the nucleus of the simplest element, hydrogen, and this is positively charged. And the others are neutrons, and neutrons, as the name somehow suggests, are neutral, so they are not charged. But the charges are accelerated by fields, and fields are either made by big magnets, like in accelerators and in tokamak, like ITER, or can be made electric fields by lasers, because the lasers also have strong fields, very locally, very short time, but then it can have very strong fields. So actually, our final goal is, of course, the microscopic mechanism is to accelerate protons. This is the relatively new branch of research, maybe 10, 15 years old, to make a proton acceleration with laser shots. Is the laser wake field acceleration, and that's what people try to do experimentally. So my expertise to this is maybe more the management expertise and the general knowledge about physics than anything specific. I mean, sure, I was trained in nuclear physics to my PhD, so I know the basic processes. And today, almost everyone knows in principle how fusion should work. But to make it technologically feasible, that's a different question.
The destruction of the equipment by the energy it is trying to contain sounds like a big problem in terms of nuclear fusion. What other kind of hurdles are you aware of, or do you think there could be to its implementation?
So fusion, we have 50 or 70 years already that we want fusion. Fusion is a natural process. Of course, we know it's going on in stars, in the center of stars, since ever the universe exists in a shape near to today's shape. But to make it artificially, to make it technically, is still unsolved in its totality. So for fusion, you need a very high energy density, a very high individual energy of individual particles. Either you reach it with high pressure at temperature, and then you need a temperature like in the middle of the sun, and the pressure. So the one branch of fusion research tries to reach it by confinement. It's called confinement. It's such a hot plasma has to be confined, and in normal metal or beton you cannot confine it. So this temperature is high over the earthly temperatures, and they confine it with magnetic fields. Of course, a confinement with magnetic fields is not easy. It's technically very much involved and costly. But this is how it's going on. And I think the biggest device built or is being built with this technology is ITER in Europe, International Thermonuclear Energy Research or Reactor Experiment. I'm sorry if I don't know what is the abbreviation. Oh, good. We had collaborators also from Germany, Horst Stöcker from FIAS, Frankfurt Institute for Advanced Studies, and also Igor Mishustin working there, and a few more guys from Russia, from Ukraine, from Germany, from Norway. So since we are an international society of researchers, we have our personal links to each other, and sometimes people join, sometimes people get out. We also have American connections with Professor Johann Rafalski from Arizona, with whom we had also common research on other topics before. Right? He was a Fulbright fellow in Budapest, and this Fulbright fellowship is signed by the President of the United States, actually. And this is by the State Department of the US. So he is a very highly appreciated collaborator for us. And just recently, he became a honorary member of the Hungarian Academy of Sciences, which is for foreign members, actually, who are non-Hungarians. The first was not me. It was two other professors, Professor Crow and Chernay, and they met at some meeting. They are both Hungarians, but Chernay was working and being a professor at the University of Bergen, Norway. And Norbert Crow was being high official of our Hungarian Academy of Sciences for decades. So Norbert is an expert on plasmons, and Laszlo Chernay is an expert on theoretical calculations with relativistic energies in materials. Relativistic hydrodynamics, they call it. And they met and they thought that these two ideas, the one idea is how to avoid instabilities at very high and very short time energy deposit. And the other was how to increase the energy density by plasmons. And they came together. They even made together some calculations and a patent with a young guy called István Pap, a young Hungarian guy who was born in Romania, but he was working together in Norway, so everyone's CV is full with some migration around the world. And that's how they started. And then Norbert thought that it would be nice to make this experimentally, not only theoretically, and what can we do in Budapest or in Hungary. And these years came that the ELI, the extreme light infrastructure, one part was implemented in Hungary, and it looked that we shall have a very high power laser soon. Now we are still waiting for that, but now we are really hoping next year it will be usable. It is there, it is just not yet used at high power. And then somehow came that we can make a project out of this. And then actually you have to go and talk different people from state secretaries, ministers, people in the Hungarian Innovation Office and so on. And then it finds out what are the possibilities at this level, at this size of budget, research financing. And then we applied and we received financing. First year, second year, now we are waiting for the next term. So if the financing stops, then we make the rest of the publications and the research will go on elsewhere. Maybe in China, maybe in Korea, you don't know. They are also doing research on fusion, I think, with very big power and with a lot of people. What the ITER wants, and we are now working on 1 billion forints, but not yearly. And this is about 1/400th of the euro or something like that. We are around 30 people and in a very delicate cooperation network. But what is costly are more the devices, not the people yet. We need very high precision detectors, we need very, very high power lasers, and we need very high contrast in making a pulse, which means it's a very low energy and it suddenly jumps, and so on. So we need very high input in the technology before we can get an output.
And then another abbreviation, another acronym of one of the organizations you're involved with is ITER, ITER. I think that's right. Could you tell us more about your involvement with them and how that came about?
We all call it ITER and very seldomly resolve this abbreviation. So the next possible way to do it, when you don't use big solenoids or tokamak devices for making magnetic fields, but you try to use laser beams. The laser beams also can make compression and also can be supplemented by energy density, but they are usually not in equilibrium and they don't need to keep long the temperature. So they are shorter shots, and in these shots the fusion should take place and then the energy harvested. So the biggest device on this track is the National Ignition Facility at the Los Alamos National Lab in the USA. I think it's about a year ago when they announced the breakthrough in their experiments, just harvesting about 70% of the energy of that what reached the final target. So we are closer to this branch, the laser ignited fusion experiments, and our goal is to improve somewhat the efficiency of energy deposition in the target. So then I start to the second main branch of the fusion research. ignites the fusion material, the fusible matter with laser pulses. Very, very high power lasers are needed to that. The biggest device is the National Ignition Facility in the Los Alamos National Laboratory in the USA. They just a year ago announced a breakthrough in their experiments in the sense that harvesting about 70% of the energy which reached the final target. You see, there are always in technology, there are always part of the energy which is lost and you cannot do anything on that, but we live on the rest, and even the rest will be very precious. So our own researches try to enhance the efficiency of the energy absorption in the target. And our main agenda for this is using nanotechnology, and in the nanotechnology make use of something what people call plasmon effects. Plasmons are collective electron motions on metal surfaces. So we implement very small metal nanoparticles, nanorods, nanoshells. We have different shapes in mind, and we ignite somehow of the plasmons on their surfaces, because the plasmons can compress the energy without needing pressure. So they simply seek the laser pulse energy and make the electric field hundreds, sometimes several hundreds bigger than it just would be in the pulse. And that means we can concentrate energy density according to theoretical estimates up to factor of 1000. If you can do that, then you need, of course, factor 1000 less power for the lasers to ignite to reach some thresholds for fusion energy. So that is our goal. And we were financed now in 2 consecutive years by a Hungarian agency. This is the National Office for Innovation, Research and Technology. And now we are just waiting for the judgment of our next 3-year plan to continue on this research.
Well, you mentioned that laser nanoplasmonics were solving, hopefully, that material science of them was solving at least one of the problems of that energy containment and its usefulness. Do you see them as maybe offering solutions to other future problems or applications outside of nuclear fusion?
That's a very good question. Of course, when you start a research, you never know what all the results will be and what about applications you can do. Of course, if we gain experience on devising the proper sized and proper material constituted nanoparticles, then of course you can be interested in concentrating energy in itself, not only for purposes of fusion ignition, right? So one of the plans are being to use nanoparticles in cancer treatment, for example, and the cancer cells, cancer tumors, then those cells are working in a much higher speed with metabolism. So if you give someone these very small nanoparticles, then those tumors will just collect them. And since they are metals, then you can heat them, all these tumors, much more than the surrounding tissue. And that means it's a possible handling beyond the direct irradiation, what people are doing today, or the chirurgical operations which you do at the end. This is one thing also other people are advocating as a possible application of nanotechnology. But our hopes are actually higher because we want to go to higher energy than that, than the chemical burning, so much higher energies. And this is also a question whether nanotechnology is able to go so far that to really realize this factor of 1000 or more energy compression, energy density enhancement, field enhancement. So what are the limits of possible field enhancement on the 100 atomic nanotechnology level is not known, and you cannot calculate it theoretically. There you need experiments to see. Of course, if you can make energy in small time and small size devices, that opens new gates for very smart technologies.
If the 2035 target is hit, well, firstly, is it likely to be hit? And if it is, then what? I suppose on the flip side of that, if it doesn't work by 2035, then what? Do we, keep going or?
Sure. I mean, of course, the first step is to have nuclear fusion artificially. So the race is now for that goal. Who has it first gets it and will be famous and gets even more money to develop. Once we have it, comes all this development question to make it smarter. How can we make fusion smarter? One is, of course, the process we are working on, whether we can make it cheaper with less input energy. This is the nanotechnology part. The second part would be something like fusion reaction chain design. What kind of fuel we put there and what kind of reaction we want to ignite. And if you can make it neutronless or without very energetic neutron, it will mean that you don't have to change the device too often. But even the first experiments, I mean, it's not an immediate damage. It will take time. You just cannot run it with the high intensity for a year or something. So it will be a problem when you want to make money out of fusion energy. But we are in the moment at the research of fusion, I think, almost everywhere, because no one is selling yet electric current made by fusion. If you make fusion, then you gain energy. And this energy then must be technologically harvested, in a sense. So everything, even nuclear fission, works in a way that the nuclear reaction and the energy coming out will make heat. It heats an environment. With the heat, you make vapor. The vapor drives turbines. The turbines are making with generators electricity. And then electricity can be distributed on a network, and everyone gets a small piece of that. So fusion also would work in such an environment. So possibly the first successful fusion experiments will end up with technological developments at the old nuclear reactors. You just exchange the uranium, plutonium, whatever you use there, nuclear fission material with the fusion fuel and then the lasers and the nanotechnology and the whole environment you would use for energy production. If you would think if you can make even smaller devices for fusion, that's how the science fiction parts comes. But this is not in 5 or 10 years, but who knows? You never know. That also can be used as motors for ships, for cars, for whatever. And then you don't have to tank for a long time. That would be some saving for us right now.
I guess, an estimate. Do you think the 2035 target is, 100% within reach? Or to be 2050? If, all things go according to plan, how attainable is?
You want the 2035 for demonstrating that we can gain more energy than putting in.
You think?
I think we are closer to that than ever. But whether the 10 years or 12 years left will be enough, I would not put my money on that. Sorry.
You don't have to be, the salesperson for nuclear fusion and tell me that it's going to be perfect, it's going to be brilliant, because life is not perfect or brilliant.
Sure. If you want private money, you tell such things. And there are already private companies financing the new ways of fusion, mostly this alternative. But if you would not research alternative possibilities, then even the main research would not go as successfully and as fast as possible.
There is, I suppose, a lot of adjustment to be made to any future that happens.
Absolutely, of course. But we have experience already with other ways of energy-driven devices and vehicles. This is a delicate issue with the collaboration because most people working, this is a very high profit at the end if someone is successful in this research. So there is a lot of concurrence, of course. We are open for collaborations to a certain level, of course, and we are even asked to collaborate with other people by our financing office and authority. So time to time, we try to find partners. But we really need partners on a just and equal footing of collaboration. So we are not intending now yet to work in, because our research is very fundamental. We are trying always to find our partners according to our next idea and next research task, what to do. In the time being, we need more partners in nanotechnology than in nuclear physics. But it will change, it may change. And laser optics, of course, but we have very good experts in Budapest on laser optics. Actually, they made the first attosecond laser. As this podcast and the article behind, we are trying to inform the public. And if someone is asking questions or a journalist is interested, we are ready to tell everything we can tell at that moment. What is established, where we are, what are our goals. Even with some agreement, if someone comes to Budapest, they can visit our lab. We can arrange things, and we are open for any discussions.